to the open channel flow sessions. We have been discussing about the most economical channel sections. Previous module, we have seen the most economical condition for the most economical channel sections, like the discharge must be maximum, and this is possible only when we have the minimum wetted perimeter. So differentiating the wetted perimeter and equating it to 0, we have found the conditions for the most economical rectangular channel section, most economical triangular channel section, most economical trapezoidal channel section. Today's class, we see about the most economical circular channel sections. So in the case of a most economical rectangular, triangular or trapezoidal channel sections, we have used the conditions like for a given channel conditions, for a given channel, the roughness coefficient is constant, the longitudinal slope is constant, and the wetted area is constant. These are the conditions that we have used, based on which we try to apply either the Chayes formula or the Manning's formula, and then arriving at the equation for the wetted perimeter for different shaped channel sections, differentiating it, equating it to 0, and we arrive at the conditions for the most economical channel sections. But for the circular channel section, we need to understand one important point. In the figure you may observe, this is the circular channel section for any arbitrary depth of flow y. For any arbitrary depth of flow y, this is the top surface, also called the free surface. As the depth of flow is increasing, what is happening? Up to the center, the top free surface also is increasing. The top weight is increasing as the depth of flow is increasing, but only up to center, beyond which, as the depth of flow is increasing, there will be convergence of boundary. That means the depth of flow decreases. So for a circular channel section of any radius, as the depth of flow varies, the shape of the flow area also varies due to the convergence of the boundaries towards the top. As such, both wetted area as well as wetted perimeter varies with the depth of flow. Hence, in the case of circular channels, we cannot apply the condition like area of flow is constant. A cannot be considered to be constant. Wetted area A cannot be considered to be constant in the case of circular channel sections. So in the case of a circular channel section, the top width T increases up to the center as the depth of flow is increasing, beyond which the top width would be reducing and converging because of the convergence of the boundaries. So the area or the shape of flow area also is varying because of this convergence of boundaries towards the top. So we cannot apply the condition that the area of flow constant. So as such, we need to determine the conditions for the maximum discharge and maximum mean velocity separately. Please try to understand what is this maximum mean velocity. We know the maximum discharge. The discharge can be maximum at certain point, and we will be able to get it. Then what about this maximum mean velocity? We know maximum velocity. We know mean velocity, also called the average velocity. But what is this maximum mean velocity? So here I would like to draw your attention once again, referring to our pipe flows. When you take a pipe flow, you must have observed different velocities like local velocity at a particular sector at a given point. At a given point is the local velocity. Then maximum velocity would be, obviously for the pipe flow, the maximum velocity is at the center. Towards the boundary, the velocity becomes reduced, and exactly at the boundary, the velocity becomes 0 following no slip condition. This is what we have learned in our pipe flows. So based on that parabolic or logarithmic velocity distribution, depending on the flow to be laminar or turbulent, we have assessed the average velocity at a given section. That is what is also called mean velocity. So we have mean velocity, we have the local velocity or the velocity at a given point, maximum velocity. There are three different things in the case of pipe flows. Here also, more or less same thing applies, that you will be having the local velocity, which can be measured with the help of a petard tube or a current meter, and the maximum velocity, which may be occurring slightly below the free surface in the case of the open channel. And of course, the average velocity always can be computed based on the velocity distribution which is given at a particular section. And the average velocity may be taken more conveniently as a local velocity at 0.22y, the local velocity at 0.8y. Take the average of both. Take the average of both. And experimentally, it has been observed that at a depth of 0.6y measured from the free surface, the velocity is close to the mean velocity or the average velocity. This is all we have learned about the velocity distribution in the case of open channel flows. Then what do you mean by this maximum mean velocity? So what are the mean velocity that you are calculating or the average velocity that you are calculating? The maximum of that, that means the condition for the maximum value of the average velocity. The condition for the maximum value of the average velocity would be SS. So similarly, the condition for the maximum value of the discharge. So in the case of circular channels, the condition for the maximum discharge, the condition for the maximum value of the average velocity of flow will be separately deduced. Okay. Further, we have two basic formulas like Cheggy's formula, Manning's formula. We may deduce the conditions making use of these two formulas. Also, try to compare the differences also. When you are using Cheggy's formula, what would be the condition, and when you are using the Manning's formula, what would be the condition? That also can be seen. Condition for maximum discharge. This part we are now trying to look at. Condition for maximum discharge through a circular channel section. Let this be a circular channel section, and the depth of flow is y. Depth measured from the free surface to the bottommost point is y. And let d be the diameter of the circular channel section, r small r is the radius, and included angle is theta. Included angle is theta. Okay, so for a circular channel section of radius small r and the depth of flow y, you will be able to compute the wetted area as well as wetted perimeter. How do we compute the wetted area? How do you compute the wetted perimeter? Going back to the fundamental definitions, wetted area is the cross-sectional area of the flow section. In the figure, you may see here, this is the entire circular channel section of which the depth of flow is y. That means the free surface is AB. AB is the free surface. So the wetted area would be the cross-sectional area of the flow section enclosed between ADBA. In this section, it is the wetted area, the cross-sectional area of the flow section. Similarly, the wetted perimeter would be the length of the channel boundary in contact with the flow. So starting from point A, ADB is the length of the arc of the circle which is in contact with flow with an included angle of theta. Okay, so length of the arc ADB gives you the wetted perimeter, and the wetted area would be the area enclosed between ADBA is the wetted area. So you need to compute the wetted area as well as the wetted perimeter. So how do you get the wetted area or the cross-sectional area of this ADBA? The cross-sectional area of ADBA. Since with respect to the center of this circle, it is making an angle of theta here. So naturally, you will be able to get the area of the arc subtended with an angle of theta. So that you will be getting the area CADBC. The entire area would be obtained, from which you will be able to deduct the area of the circle CAB. Area of the circle CAB. So area CADB minus area of the triangle CAB provides you the wetted area. Similarly, the wetted perimeter will be the length of the arc subtended. That means the length of the arc ADB. R is the radius. Of course, r multiplied by theta would give you the wetted perimeter. So you need to compute the wetted area and the wetted perimeter. Let us see how can we compute these two for the given circular channel section. So the top width for this, how do you get the top width? So in this triangle, the included angle is theta. So for any triangle like you are taking CD dash A, if you take, this included angle becomes theta by 2. This included angle becomes theta by 2. And since R is the radius, CA would be equal to R, CB also would be equal to R. CA or CB would be equal to R. So if you take sin theta by 2, sin theta by 2 would be equal to D dash B divided by CB. CB is R. So R sin theta by 2 is the half of the top width. Similarly, this side also R sin theta by 2 is the half of the top width. So the top width AB would be equal to R sin theta by 2 on the left hand side plus R sin theta by 2 on the right hand side. 2R sin theta by 2 would be the top width. And CD dash, this portion, CD dash would be R cos theta by 2, quite obviously. So you have 2R sin theta by 2, the top width, and R cos theta by 2 is CD dash. Why this CD dash is required? Because you need to compute the area of the triangle CAB. Area of the triangle CAB, which is required to be deducted from the area of the arc. Area of this arc. So we need CD dash. It is R cos theta by 2. And the top width is AB, which is equal to 2R sin theta by 2. And CD dash is R cos theta by 2. So the vectored area by definition is the cross-sectional area of the flow section, which is equal to area CADBC minus area CBC. Area CABC. Area CADBC minus area of the triangle CABC. So to get this area of this, your theta by 2 pi into pi r square. Theta by 2 pi into pi r square. What is theta? Theta is the angle in radians, right angle BCA. Okay, so theta by 2 pi into pi r square is the area of the arc minus half area of the triangle. So half of base into height. Half of 2R sin theta by 2 into R cos theta by 2. So simplifying this, you will be getting theta by 2 into R square. Pi gets cancelled here. Theta by 2 into R square minus R into R. So R square by 2 into 2 sin theta by 2 cos theta by 2. So 2 sin theta by 2 cos theta by 2 is sin theta. So you have theta by 2 into R square minus R square by 2 into sin theta. Take out R square by 2 from both the things. R square by 2 into theta minus sin theta is the vectored area. In the earlier case also, when we are computing the open channel flow circular channel sections while applying the Chayes and Manning's formula, we have obtained the equation for the vectored area as well as vectored perimeter. But for the sake of convenience, those who are missing in the earlier classes, they also can listen once again. So I am repeating as if it is fresh, as if it is new. I am repeating how to compute the vectored area for a circular channel section. Okay, so vectored area R square by 2 into theta minus sin theta. Similarly, vectored perimeter would be the length of the arc subtended. So included angle theta. So R into theta gives you the vectored perimeter. Now you have got two equations, vectored area as well as vectored perimeter. Theta is the angle subtended at the center portion of the circular arc, which is in contact with water. Now use Chayes formula. So according to the Chayes formula, V is equal to C into square root of RS, or the discharge Q will be equal to CA into square root of RS. CA into square root of what is R? Hydraulic radius, A by P into S. CA square root of A by P into S. Or take this A inside, it becomes A square under square root. So it will be C into A square into A cube by P into S. Where S is the bed slope, C is the Chayes coefficient, both are considered to be the constant, and hence the discharge Q would be depending directly on A cube by P. Discharge Q depends on A cube by P. For the discharge Q to be maximum for the most economical channel, A cube by P must be maximum. A cube by P must be maximum. Just compare this with the earlier cases of rectangular, triangular, trapezoidal. A was not considered that. A also was considered to be constant there. And the discharge Q would be maximum and P is minimum. That was the condition that we have used. But now here, since A also due to the convergence of the boundary, A also is changing the shape of a flow, and hence A cube by P must be maximum for the discharge Q to be maximum. Hence, differentiate A cube by P with respect to theta and equate it to 0. So differential of A cube by P with respect to theta. So d by d theta of A cube by P must be equal to 0. D by d theta of A cube by P. So it's something like U by V, UV dash minus VU dash by V square. Okay. So A cube, A and P both are functions of theta, and hence P into differential of A cube minus a cube into differential of p divided by p square. So p into differential of a cube 3a square into differential of a dA by d theta. Differential of a with respect to theta dA by d theta. So p into differential of a cube 3a square dA by d theta minus a cube into differential of p dp by d theta divided by p square is equal to 0. Is equal to 0. We need to simplify this equation by substituting the appropriate values of a and p in this. Okay, so take this p square to the right hand side. Take this p square which is in the denominator to the right hand side. It becomes 0 into p square. So you have p into 3a square dA by d theta minus a cube into dp by d theta must be equal to 0. Even in this also, you have a square here in the first term, you have a cube in the second term. Take out a square common and take to the right hand side, so that you will be having 3p into dA by d theta minus a into dp by d theta would be equal to 0. 3p into dA by d theta minus a into dp by d theta would be equal to 0. Now you are left with 4 parameters here. One is p, the vector perimeter, dp by d theta, its differential, a, vector area, dA by d theta, its differential. So if you know all these 4 values, you can substitute in this equation and solve for theta. So look at this. P, A, we know very well. What is P? Vector perimeter r into theta. We already obtained the condition. And A, vector area r square by 2 into theta minus sin theta. So A is r square by 2 into theta minus sin theta. So dA by d theta, its differential will be r square by 2 into 1 minus cos theta. R square by 2 into 1 minus cos theta. Similarly, P, which is equal to r theta. So dP by d theta will be r. So you have now the equations for vector area A, dA by d theta, vector perimeter P, dP by d theta. Substitute all the 4 in this equation. 3p dA by d theta minus a into dP by d theta is equal to 0. Substitute here. So 3 into P r theta into dA by d theta r square by 2 into 1 minus cos theta minus what is the equation? Minus a into dP by d theta. A is r square by 2 into theta minus sin theta into r must be equal to 0. Try to simplify this equation. As you simplify this equation, you will be getting r cube, and r cube gets cancelled here. 2 also gets cancelled. You have 3 theta into 1 minus cos theta minus theta minus sin theta must be equal to 0. In other words, 3 theta minus theta, 2 theta minus 3 theta cos theta plus sin theta is equal to 0 is a trigonometric equation. Solving for this equation, theta is equal to 308 degrees. So what you have done now? We have obtained a condition for the maximum discharge in a most economical circular channel section. For a most economical circular channel section, the value of theta must be equal to 308 degrees. But please note that what equation we have used here? We have used Chedge's equation. Q is equal to CA root RS, or V is equal to C into square root of RS, based on which the discharge Q would be equal to CA into square root of RS. Using that equation, we have obtained the condition for the most economical circular channel section for maximum discharge as theta is equal to 308 degrees using Chedge's formula. Then for maximum discharge, the depth of flow. Now you have got the value of theta. So what is the depth of flow? The depth of flow in the channel y would be equal to r minus r cos theta by 2. So substituting that, you will be getting r plus r cos 180 minus theta by 2 or r into 1 plus cos 26 degrees, which is 0.95 times the diameter. What does it mean? If d is the diameter of the circular channel, the depth of flow must be 95% of the diameter. 0.95 times the diameter, then you will be getting the most economical circular channel. So you can see here in this picture, this is a circular channel. Arbitrarily in the rear case, what we have done, we have taken the free surface, the top water surface below the center, but actually it is 0.95 times. Y must be 0.95 times the depth of flow, almost nearer to the apex peak. Okay, so 0.95 times d when the depth of flow is 0.995 times D, you'll be getting the most economical circular channel. Correspondingly, the included angle you may note here. In the figure, you may note here the included angle is 308 degrees at this circle. At the point of the center of the circle 360, but the included angle is 308 degrees. In such case, you will be getting the most economical circular channel section and the condition for the maximum discharge using Cheggy's formula. Corresponding hydraulic radius R would be A by P. A R square by 2 into theta minus sin theta divided by P R theta. R gets cancelled both in denominator and numerator. So your R by 2 theta into theta minus sin theta. Substitute for theta being equal to 308 degrees. So correspondingly, if you convert this into radius, pi by 180 into 308, and correspondingly the value of the hydraulic radius is 0.29 times the diameter. 0.29 times the diameter. Till now, we assessed the condition for the maximum discharge in a circular channel using Cheggy's formula. Using Cheggy's formula. Now, if you use Manning's formula, how it would be different also? Let us see. Q, the discharge 1 by n, A r power 2/3, s power half, 1 by n, A r power 2/3, r is how much? A by P. A by P. That means if you take A also inside, then it will be A to the power 5 by P square whole to the power 1 by 3. 1 by 3. Because you have A to the power 2 by 3 plus A to the power 1. So you have A to the power 5 by 3 divided by P to the power 2 by 3. So A to the power 5 by P square whole to the power 1/3 into s power half. Now, for discharge Q to be maximum for the given values of n and s, for the given values of n and s, A to the power 5 by P square must be maximum. So differentiate A to the power 5 by P square with respect to theta and equating it to 0. So d by d theta of A to the power 5 by P square must be equated to 0. Same thing what we have done in the earlier case, we have applied here also. So something like a differential of u by v, v into u dash minus u into v dash divided by v square. So p square into differential of A to the power 5 minus A to the power 5 into differential of P square divided by P square whole square. So it will be P to the power 4. It will be P to the power 4. So P square into differential of A to the power 5. 5A to the power 4 into differential of A with respect to theta dA by d theta minus A to the power 5 into differential of P square. Differential of P square. So 2P into dP by d theta. So this P to the power 4 in the denominator taking to the right hand side becomes 0. And in this also you have A to the power 4, A to the power 5. So A to the power 4 can be taken out and take to the right hand side. You are left with the equation 5P dA by d theta minus 2A dP by d theta is equal to 0. In this, again, we have 4 parameters. Vector area A, dA by d theta. Vector perimeter P, correspondingly dP by d theta. So if you substitute the values of A, dA by d theta, P and dP by d theta in this equation, you will be getting a trigonometric equation 3 theta minus 5 cos theta plus 2 sin theta must be equal to 0. And solving this equation, the value of theta is 302 degrees. What was the earlier corresponding value? Using Cheggy's formula, theta is 308 degrees. Using Manning's formula, it is 302 degrees. Why there is a difference? There is a difference because both these formulae, let it be Cheggy's formulae, let it be Manning's formulae, both are semi-empirical formulae which have been developed based on several different criteria. So Cheggy's coefficient in the case of Cheggy's formula, Manning's coefficient in the case of Manning's formula are interdependent on various factors. As a result of which, you have the value of theta different. While using the Cheggy's formula, you have the value of the theta different, another value while using the Manning's formula. While using Manning's formula, theta is 302 degrees for the maximum discharge, and while using Cheggy's formula, theta is 308 degrees. 308 degrees. Correspondingly, the depth of flow will be r plus r cos 180 minus theta by 2. Substituting the value of theta to be equal to 302 degrees, you will be getting 0.938 d. In the earlier case, it is 0.95 d. The depth of flow is 95% of the diameter of the circular channel. Whereas here, the depth of flow is 94% of the diameter of the circular channel to get the maximum discharge. So we have seen now the condition for maximum discharge using Cheggy's formula, using Manning's formula in a circular channel section. Now we deduce the condition for the maximum value of the average velocity of flow in a circular channel section. According to Chegis and Manning's formula, the mean velocity of flow through the circular channel is proportional to the hydraulic radius A by P. So you have A by P, d by d theta of A by P must be equal to 0. So the condition for the maximum value of A by P will be differential with respect to theta and equating it to 0. So d by d theta of A by P must be equal to 0. Or P into d A by d theta minus A into dP by d theta by P square must be equal to 0. Must be equal to 0. Take this P square to this side. Substitute the values of A, P, dA by d theta and dP by d theta. Substitute all the values. A, P, dA by d theta, dP by d theta. A is r square by 2 into theta minus sin theta. P is r into theta. dA by d theta r square by 2 into 1 minus cos theta. And dP by d theta is r. So substituting these values here, you will be getting an equation theta is equal to tan theta. Solving this equation, the value of theta is 257 degrees and the corresponding depth of flow will be r plus r cos 180 minus theta by 2. Substituting that, you are getting 0.81 d. So this is the condition for maximum velocity. Condition for maximum discharge 0.95 d using Chegis formula, 0.94 d using Manning's formula. Condition for the maximum velocity is 0.81 d and the corresponding value of theta is 257.5 degrees. So the corresponding hydraulic radius r is 0.3 d. In all the cases, d is the diameter of the circular channel section. So we have seen now the condition for the maximum discharge, the condition for the maximum value of the mean velocity. Why these two conditions are separately reduced? Because in the case of a circular channel, we cannot apply the condition that the area of flow section is constant, since there is convergence of boundaries. The shape of a flow area would be changing with respect to center and above the center of the circular channel section. As a result, you cannot apply the condition the area of a flow constant. Since A is also variable with respect to the wetted perimeter P, we have the conditions like A cube by P or A to the power 5 by P square, and the differential of which with respect to theta must be equal to 0, and applying the conditions of the wetted area A, equations for the wetted area A, wetted perimeter P, dA by d theta, dP by d theta, we would be arriving at the values of theta and the depth of flow for the maximum discharge using Chegis formula, using Manning's formula, and maximum mean velocity. Maximum mean velocity. Let us work out some of the problems. May not directly be related only to the most economical conditions, but the general geometric conditions applying the uniform flow also are given here. Let us try to understand and work out as many problems as possible on the circular channel sections. Water flows through a circular channel at a rate of 400 liters per second when the channel is having a bed slope of 1 in 9,000. The depth of water in the channel is 0.8 times the diameter. Find the diameter of the circular channel if the Manning's n is 0.015. Let us try to understand what is this problem. Water flows in a circular channel. So it is given that it is a circular channel section. At the rate of 400 liters per second, the discharge is given 400 liters per second. That means 400 divided by 1000 meter cube per second. 1 meter cube is 1000 liters. So 0.4 meter cube per second is the discharge Q. The channel is having a bed slope of 1 in 9,000. So longitudinal slope S is given 1 by 9,000. The depth of water in the channel is 0.8 times the diameter. So why the depth of flow in the figure you may see, why the depth of flow is 0.8 times the diameter. So up to the level ACB, the water is there in the circular channel section, and ACB is the free surface. ACB is the free surface. Find the value of D if the Manning's n is given to be 0.015. Since Manning's n is given, we have to apply the Manning's equation. In the circular channel, you may observe O is the center of the circular channel and the depth of flow is 0.8 times the diameter, while D is the diameter of the circular channel, 0.8 times the diameter up to which it is filled with water. So ACB is the free surface. ACB is the free surface. Then if 2 theta is the included angle here, 2 theta is the included angle here, correspondingly the water level is up to ACB. The water level is up to ACB. So in this triangle, you may note down, you may see here the included angle alpha is with respect to OC. With respect to OC, you have the included angle alpha. OA or OB would be equal to the radius d by 2. The radius r, which is equal to d by 2 of the circular channel. And AB is the top width. AB is the top width. So the discharge Q 0.4 meter cube per second, 400 liters per second. So 400 divided by 1000 meter cube per second. 1 meter cube is 1000 liters. Longitudinal slope S is 1 by 9000. Manning's coefficient N is 0.015. The depth of flow Y is 0.8 times the diameter. 0.8 D. 0.8 D. Okay, then from the figure, what is OC? From the figure, what is this OC? The OC would be equal to CD minus OD. If this is C, CD minus OD. So you will be getting 0.8 D, the total diameter, and 0.5 D is the radius. You may observe here, the total is D. The total is D. And this is 0.8 D, which gives that the up to center it is 0.5 D, and the remaining is of course 0.3 D. So OC is 0.3 D in this figure. OC is 0.35 D. 0.3 D, sorry, 0.3 D. And what is OA? OA is 0.5 D because it is the radius, half of the diameter, 0.5 D. You will be able to get AC. How much would be AC when this is 0.5 D and this is 0.4 D? This can be computed. 0.3 D here, so this can be computed. Further, the included angle is alpha. The included angle is alpha. So you will be able to compute AC would be OA square minus OC square, 0.5 D whole square minus 0.3 D whole square under square root. So you have 0.4 D. AC will be 0.4 D. So 0.3, 0.4, 0.5. As simple as that in this triangle of OAC. In the triangle of OAC. Compute tan alpha. AC by OC. 0.4 D by 0.3 D. 1.33. Alpha is 53 degrees. Theta would be 360 minus 2 alpha. Because the total is 2 theta that we have taken include angle. So theta would be 360 minus 2 alpha. So 253 degrees is the total included angle. A is r square by 2 into theta minus sin theta wetted area. And wetted perimeter P is equal to r theta. R is equal to A by P hydraulic radius. Then substitute in the discharge equation Q is equal to 1 by N. A r power 2/3 S power half. Substituting these values for the discharge, for the wetted, for the resistance coefficient N and wetted area, hydraulic radius, you will be able to get D. Solve for D. So the value of D is 1.266 meters. One more problem. Find the discharge of water through the channel shown in figure. What is the shape of this channel? It is not simply a rectangle. It is not simply the circular. These type of channels are called composite channels. In most of the instances, composite channels would be used in view of its economy and freedom in laying the channels. We go for this type of composite channels. Find the discharge of water through the channel shown in figure. Take the value of changes constant 60, slope 1 in 2000. 1 in 2000. You see the shape of the channel is given like this. A, B, C, D in the figure. A, B, C, D is a rectangular portion. And B, E, C is a circular portion. B, E, C is the circular portion. So combination of these two is a composite channel. Further, what is given here? The depth of flow is given to be 2.7 meters. 2.7 meters. So from the free surface to to the bottommost point, it is 2.7 meters. Further, it is given that the radius of this circle, the radius of this circular portion of the channel, 1.5 meters. Since R is 1.5 meters, we have OE also is 1.5. So 2.7 minus 1.5, 1.2 is the depth of flow in the rectangular portion. So how to compute wetted area? To compute the wetted area, it is the cross-sectional area of the flow section. So you should take the cross-sectional area of the rectangular portion, ABCD, plus the cross-sectional area of the semicircular portion, BEC. So cross-sectional area of the rectangular plus cross-sectional area of the semicircular portion gives you the total wetted area of the flow section. How to get the wetted perimeter? Please note, the wetted perimeter would be length of the channel boundary in contact with flow. So there is no boundary for the rectangular channel BC here. There is no boundary. It is directly connected to this is the semicircular channel. So by definition, length of the channel boundary would be AB plus BEC plus CD. I repeat again, the length of the channel boundary would be AB plus BEC plus CD will be the length of the channel boundary in contact with the flow. So accordingly, the wetted perimeter P should be computed. Please note that the wetted perimeter for the composite section is not equal to the wetted perimeter of rectangular plus wetted perimeter of circular. You should not use that. However, for the wetted area, it is fine. The cross-sectional area of the rectangular portion plus the cross-sectional area of the semicircular portion gives you the total wetted area. But for calculating the wetted perimeter, you should go by the basic fundamental definition. The definition is length of the channel boundary in contact with the flow. So the channel boundary here is AB plus BEC plus CD. So that is the channel boundary, and hence you have to compute the wetted perimeter as ABECD. Length ABECD. That is the wetted perimeter. Okay. Once you get the wetted area and the wetted perimeter, remaining things are so simple. Since Manning changes coefficient is given using changes formula, the discharge Q, which is required to be found in this problem, is equal to CA square root of RS. CA square root of RS. C, changes coefficient is known, 60. A, wetted area which we have computed as sum of the rectangular plus semicircular portions. Wetted perimeter P and hydraulic radius R is equal to A by P, and then longitudinal slope S is given to be 1 by 2000. Okay, so the longitudinal slope is given to be 1 by 2000. The changes coefficient C is 60. Wetted area A would be equal to area of the ABCD, that rectangular portion, plus area of the semicircular portion. So rectangular portion 2 into 1.5 plus the area of the semicircle pi by 2 into R square, pi R square by 2. R is 1.5, so pi R square by 2. So 3 into 1.2 plus pi by 2 into 1.5 square, 7.1 square meters is the wetted area. Wetted perimeter, length of the channel boundary in contact with the flow. So two sides, 1.2 plus 1.2 plus 2 pi r is the total perimeter of the circle, but it is a semicircle, so pi r. Perimeter is pi r. So 2 into 1.2 plus pi into 1.5, 7.1 meters is the wetted perimeter. Hydraulic radius will be A by P. So 7.134 divided by 7.1124, 1.003 meters is the hydraulic radius. Once you get the value of the hydraulic radius and wetted area, make use of the changes formula. Discharge Q is equal to CA square root of RS. CA square root of RS. Changes coefficient C 60 into wetted area 7.134 into hydraulic radius 1.003 into S is 1 by 2000 longitudinal. So 9.585 cubic meters per second. 9.585 cubic meters per second is the discharge. One more problem. Find the diameter of the circular sewer pipe. What is a sewer pipe? It's a drainage pipe which carries sewage. Which carries sewage is the sewer pipe. So usually the sewer pipes would be circular in section and they will be buried underground. They will be buried underground. The diameter of the circular sewer pipe, which is laid at a slope of 1 in 8,000, the longitudinal slope is given, S is 1 by 8,000, carries a discharge of 800 liters per second when flowing half full. Try to understand the meaning of this. When flowing half full, so it is a circular pipe and the water is exactly up to the center. It is running half full. So the depth of flow Y would be equal to diameter divided by 2. Diameter divided by 2. The Manning's coefficient is given to be 0.020 and the discharge is 800 liters per second. And you need to find the diameter of the circular pipe. You need to find the diameter of the circular pipe. Further, the Manning's coefficient is given. So make use of the Manning's formula. The discharge Q is 800 liters per second or 800 divided by 1000, 0.8 meter cube per second. N is 0.02. D is the diameter of the sewer pipe. So the depth of flow is given half full. It is running half full. So Y is equal to D by 2. Cross-sectional area of the flow section or wetted area would be half of the area of the circle. Half of the area of the circle. So pi by 4 d square into 1 by 2. Pi by 8 d square is the wetted area. Wetted perimeter is, once again, half of the perimeter pi r or pi d by 2. Wetted area by wetted perimeter gives you hydraulic radius. R is equal to A by P, which is equal to D by 4. So substituting, the discharge Q is 1 by N, A R power 2/3, S power half, 1 by N, 0.02, A wetted area pi d square by 8, hydraulic radius R is D by 4, and S is 1 by 8,000. So substituting the values and simplifying, you are getting the diameter to be equal to 2.296 meters. Find the discharge through a circular pipe of diameter 3 meters. If the depth of water in the pipe is 1 meter and the pipe is laid at a slope of 1 in 1000, take the Chayes coefficient. C is equal to 70. Once again, you require to find the discharges. Several problems have been worked out because I thought you need to get more and more practice in working out these different shaped channels and different conditions, like calculating the discharge, calculating the diameter of the pipe, calculating the longitudinal slope, and so on. Okay, so this is a circular channel section, and you need to find the discharge, and the diameter of the pipe in this case is given to be 3 meters, and the depth of water in the pipe is only 1 meter. It is not up to the center also, it is below. So Y is 1 meter, whereas D is 3 meters. So the radius of the pipe is 1.5. 1.5. So OC in this case becomes 1.5 minus 1.5 meters. 1.5 minus 1.5 meters. The slope is given 1 in 1000. Chayes coefficient is given. You are required to find the discharge. So since Chayes coefficient is given, make use of the Chayes formula. So C is 70, S is 1 by 1000, and Y is given to be 1 meter. Wetted area R square by 2 into theta minus sin theta, theta minus sin theta, and wetted perimeter P is R into theta. R into theta. Please note that the value of theta is substituted in radians, and you have got the wetted area, you have got the wetted perimeter, and hence the hydraulic radius is A by P, 0.55. Substituting in the Chayes equation using the discharge equation, Q is equal to CA square root of RS. Substitute for the value of C, wetted area 2.06, hydraulic radius 0.55, and longitudinal slope 1 by 1000. Don't get confused with this X. This is into. Okay. Now you have got the discharge Q is equal to 3.4 meter cube per second. In the above problem, the depth of water is 2.5 meters. Then what is the rate of a flow? In the earlier case, it is given 1 meter out of 3 meters. Now it is 2.5 meters. Depth of flow is come up to this level. So out of 3 meters diameter, 2.5 meters is the depth of flow. Then you need to compute what would be the discharge. What would be the discharge? Follow the same procedure. Follow the same procedure. Only thing is, while arriving at the value of theta, you need to be careful. Once you get the value of theta, the remaining things are same. Okay, R square by 2 into theta minus sin theta, and then substituting here, you are getting the wetted area 6.2 meter cube. Wetted perimeter P is equal to R into theta 6.9. Hydraulic radius will be A by P 6.2 by 6.9, 0.9 meters, and the discharge Q is CA square root of RS. C 70, wetted area 6.2 into square root of hydraulic radius r is 0.912 into 1 by 1000. This is not x, into 1 by 1000, 13.303 meter cube per second. Then the rate of flow of water through a circular channel of diameter 0.6 meters is 150 liters per second. Find the slope of the bed of the channel for maximum velocity. Here is the condition that you need to make use. Condition for maximum velocity. So this is a circular channel. The diameter is given 0.6 meters and the discharge is 150 liters per second, or 150 by 1000, 0.15 meter cube per second. And you need to find the slope for maximum velocity. You need to find the slope for maximum velocity. So what is the condition for the maximum velocity? The condition for the maximum velocity is the depth of flow must be 0.81 times d and the value of theta must be 257 degrees. So making use of that, theta 257 into pi by 180 gives you 4.494 radians. 4.494 radians. And r would be 0.3 d or 0.18, and wetted perimeter p is equal to r theta 0.3 into 4.496, 1.3483 wetted perimeter. R is equal to a by p, and wetted area is r square by 2 into theta minus sine theta. Substituting those values, you got 0.24 meters square. So the discharge Q would be equal to Ca square root of Rs 0.25, 0.15, the discharge 150 liters given, into changes coefficient C60, wetted area 0.24 into square root of 0.18 hydraulic radius into S required to be found. This is not X, this is into S. S is the longitudinal slope. S is found to be 1 by 1625 is the longitudinal slope. This is to carry the maximum velocity in the channel. So we made use of the condition for maximum velocity. What are the conditions for the maximum velocity? The value of theta is 257 degrees and the depth of flow y is 0.81 d. The depth of flow is 0.81 d. Hydraulic radius is 0.3 d. So we made use of these conditions, substituted here to get the longitudinal slope. Determine the maximum discharge of water through a circular channel of diameter 1.5 meters when the longitudinal slope or bed slope of the channel is 1 in 1000. Changes C is given to be 60. So C is 60, diameter is 1.5, and since diameter is 1.5, the radius is 0.75, S is 1 in 1000, find the value of the discharge Q. So it has to carry the maximum discharge. Please note here, condition for maximum discharge you have to use. Further, changes coefficient is given. So while using the changes coefficient, what is the condition for maximum discharge? The condition for maximum discharge is theta is 308 degrees. Theta is 308 degrees and the depth of flow y must be equal to 95% of capital D, 0.95 d. These are the two conditions. Accordingly, theta is 308 degrees, or theta in radians will be 308 into pi by 180. So 5.376. Wetted area r square by 2 into theta minus sine theta, and wetted perimeter p is equal to r into theta. Hydraulic radius r is a by p. So substitute those values here. You are getting the discharge Q. You are getting the discharge Q. We worked out several problems. Some of the problems relating to the application of the simple uniform flow formulae like Chayes formulae and Manning's formulae, finding the discharge, finding the diameter, or finding the longitudinal slope and so on. Secondly, making use of the conditions for the most economical circular channel section for velocity as well as for the discharge using Chayes formula. Okay, so we finished about the most economical sections. With this, we have taken up 4 conditions: most economical rectangular, triangular, trapezoidal, and circular channel sections we have seen. I hope we have completed the major part in the open channel uniform flow.